Hey folks, Mr. Ray here. We're going to continue on with our solving exponential and logarithmic equations. Um, in the previous lesson we looked at coming up with a common base on both sides of the equation if possible, and then using that approach. So we're going to look at a couple of slightly more complex methods. Okay. Now we're going to start off with a word problem here. So hopefully you remember your exponential functions unit from grade 11. You had some growth and decay problems using exponential functions. One of the more common ones was the half-life for radioactive material. Okay, so this could be a question we had from grade 11, but we're going to solve it a slightly different way than you probably learned in grade 11. So polonium-218 is a radioactive substance, spontaneously decays into lead-214. 1 minute after a 100 milligram substance of this is placed into a nuclear chamber, only 80 grams remains. Okay, determine the half-life. So I'm gonna start off with the basic equation, which is the generic variables. So use a capital of A for amount remaining is equal to the original amount, A subscript 0 or O maybe, and then our because we're trying to find the half-life, our base is going to be 0.5 because we're multiplying over and over by half or 0.5, and then we have 1 over the half-life, which we don't know. That's what we're actually going to try to find. Okay, so at this point now we can go back and pull in some information. So it does say we don't really have to do anything with these actual element names. Okay, but the key things here is after 1 minute, after 100 milligram substance is placed, only 80 milligrams remains. So we're starting off with 100 milligrams, so that would be the original amount, and we end up with 80 as the current amount. So start with 100, get 80, and then we have our 1 over the half-life. Okay, and there's a little bit of math we can do here. We can actually divide both sides by 100 to get rid of this. So when we do that, we get 0.8 is equal to 0.5 to 1 over HL. Okay, and at this point you go, well, what do we do now? Okay, so this is an exponential equation. We're trying to actually solve for the exponent. So this is where logarithmic equations would come in really handy. So we're actually going to change this from its exponential form to the logarithmic form. Okay, so if you remember, there's 3 elements to the logarithmic equation and the exponential equation. We have the result, we have the base, and we have the exponent. So when I rewrite this as a logarithmic equation, I'm solving for the exponent because a log is an exponent. So I start off with whatever the exponent is. So 1 over HL is equal to the log, and then now we put the base in. So the base for the log is the same as the base for the exponential equation. So that's 0.5. And we take that log of the result. So log of 0.8. I could put this in brackets if I want, just to separate it from there. So now we've at least got our variable by itself, although it's the reciprocal, but we can deal with that. So how do we get the log using this base? Well, we have to use the change of base rule. So we can rewrite it as 1 over HL is the log of the result over the log of the base. So log of 0.8 over log 0.5. Now, how do we deal with this? Well, the best way is to think about it. If I flip the left side and I flip the right side, it's still equal. So if I flip the left side, I get HL over 1, or just HL, which is the half-life. And if I flip these, it's now the log of 0.5 over the log of 0.8. Okay, and the answer when you put in your calculator is 3.11 minutes. Okay, and then the second part asks for a sketch of the graph. So we know this is a decaying function over time. So we have our time here in minutes. Start at 0, and the original amount. So this is the amount in milligrams. So we started at 100, and so I want to put 80 here somewhere. So we got 80, 60, 40. That's not going to work. So 80, 60, 40, 20. Okay, and in terms of time, well, let's see what we've got. So we do know at the start of this experiment, we started with 100 milligrams, and after 1 minute, so I've got my scale down here. So that's 1, 2, 3, 4 minutes. So we know after 1 minute, so that's 60, 80, 40, 20. After 1 minute, we have 80 left. So there's definitely a point on the graph. And we actually do have another point, because the half-life tells us after 3.11 minutes, we'll have half of what we started with. Okay, so 3.11 would be a little bit to the right of here, and I know I'm going to have 50 milligrams at that point. Okay, so that gives us a good idea of, what does this curve look like. So it's going to be going down towards here, and this will be an asymptote. The y equals 0 will be an asymptote. It'll get closer and closer, but not ever really get to 0 theoretically. Okay, so that is the graph of that. All right, let's try some equations now to solve. Some just base equations without any word problem around it, to learn some new techniques. Okay, so this one I'm going to need a little bit more room. I should have probably left some more space, but I need some space for this too, just to warn you. So we've got solved the equation 4 to the power 2x minus 1 is equal to 3 to the x plus 2. So if you remember last lesson, we saw some similar examples, but the difference was, we might have instead of a base 3 here, we'd have a base 2, and we could change, keep that as a base 2 and change this to a base 2. So we had numbers that were, working well with each other in terms of coming up with a common base and then just setting the exponents equal. In this case, we can't do that. I can't change either of these to a lower base. I can't change them to a 2. So that eliminates that option. So this technique, what we actually do is we take the log of both sides. So it's kind of like taking the square root of both sides, okay? And you'll see why this works so well. So I take the log of 4 to the 2x minus 1, and that's going to be equal to the log of 3 to the x plus 2. Like I said, it's just as long as we do the same thing to both sides, the equation is still valid, it's still balanced. So taking the log, like I said, is sort of equivalent to taking the square root or taking the sine of both sides, something like that. Okay, now here's where our logarithm laws come in. So remember when we had taking a log of something to a power, we could actually use the power law, and that causes the exponent to actually come out as a multiplier of the log. Okay, so in this case, we get a 2x minus 1 multiplying with log base 4. And the 2x minus 1 is gone because it's moved over here. To do the same thing here, the x plus 2 exponent, we can now put it in front of the log as a multiplier. And we end up with x plus 2 times log 3. Okay, it's very, very important to put brackets around this if this is more than one term, because this whole thing is multiplying with log 4. If I did not put brackets around here, you would lose that fact. So same thing over here. That's probably one of the more common mistakes on a question like this. At this point, so what we're trying to do is solve for x, but I've still got, an x pretty embedded into both sides. So I'm going to try to expand this so I can separate terms. So it's really just, using distributive property. I have 2x times log 4 minus log 4, minus 1 log 4. You can just write as minus log 4. And then I've got x log 3 plus 2 log 3. So it's starting to look a little better. But I've still got, if I look where my x's are now, I've got one here, one here. So the next goal will be to put all the terms with x's over on the left side and all the terms that don't have x's over on the right side. So basically it means I'm going to subtract this from both sides, keep this here. So I've got 2x log 4 minus x log 3. And I want to clear this out, so I'm going to add log 4 to both sides. This is gone because I subtracted it. So I've got 2 log 3 plus log 4. Log 3 plus log 4. Okay. So now we've got, our x's are only on one side, so that's a step in the right direction. And you can see right now I could actually factor the x out of both of these terms. And that's an important step because it allows us just to have the one x now. So if I factor the x out of here, I get a 2 log 4. If I factor it out of here, I get minus log 3. And leave the right side the same. Okay, need some more room, so I'm going to go back up over here. Okay, so now you can see, hopefully, all I'm going to do is divide both sides by this factor, multiplier of x, and that will isolate the x. So I keep this over here, 2 log 3 plus log 4. And then divide both sides by 2 log 4 minus log 3. Okay. And for me, I'm totally okay with this as well, if I'm asking for the exact value, and I wasn't really clear here, in this case, we're actually going to solve for an approximate value. So we're actually going to evaluate what this is in terms of a number. This by itself is the exact value. So if the question says, give the exact solution for this, then you would leave it like this. There's one more thing you can do here. Okay, and this is kind of using the power law for logarithms in the kind of the opposite direction. Since I have a 2 in front of here, 2 log 3 is the same as log 3 squared. And 3 squared is 9. So I could rewrite 2 log 3 as log 9. And plus log 4, I can't do much with that. And also the 2 log 4 I can rewrite as log 4 squared, which is log 16 minus log 3. So a lot of teachers like you to, to do this step here. I'm okay with either form. It looks a little more simplified here, but either way it's good. Now at this point, if you put this in your calculator, now if we round it to 2 decimal places, we're going to get 2.14. Okay, and again, you could go back to the original equation here, plug the x in, and make sure they're equal. But again, since we've actually rounded going from here to here, it's probably not going to be exactly the same on both sides. It might be off by, you know, 1/100th or something like that. The other thing I want to say about this is when I took the log both sides, it was kind of an arbitrary decision. Well, which base am I going to use? I decided I'm going to use the common log because I've got this button on my calculator. But I could have also used the ln function, ln, using the base e. And you have a ln button on your calculator as well, which is usually right beside the log button. So I could have done the same thing and just replaced the log with ln for ln all the way through here. And if you got to here and you had ln 9 plus log 4 over ln 16 minus ln 3, you would still get the same answer. Okay, so either taking the common log or the natural log, ln, is an option for this question. A lot of teachers prefer you to do ln, but again, I know either method will work. Okay, this question here, this is probably one of the trickier ones in, well, this is an exponential equation. So let's look at this. We have 2 to the power x minus 2 to the power negative x equals 4. Okay, and you can kind of tell here, it says apply the quadratic formula. So the way it's written here, I definitely can't do that. I'm going to have to do a couple of tricks. So I'm going to show you the technique. I wouldn't expect you to come up with this by yourself. If you did, my hat's off to you. But this is a little tricky. So what I'm actually going to do, I don't really want to work with that negative x as an exponent. So what I'm going to do is I'm going to multiply both sides by 2 to the x. So every term gets multiplied by 2 to the x. So I've got, I'll put these in brackets just so it's a little clearer what's going on. 2 to the x times 2 to the x minus 2 to the negative x times 2 to the x equals 4 times 2 to the x. Okay, so what's going to happen here? Well, we can both of these have a common base, so we could use our product rule. So we'd end up adding the two exponents. So this is going to be equal to 2 to the power x plus x, which is 2x. And this, when I add them together, I get a 0. So this is minus 2 to the power 0, which actually is 1. And that's going to be equal to, now I'm actually not going to combine these. You could probably see I could change that to 2 squared and then combine it, but that's not going to work for this technique. So let's see what we're going to do. So I'll just leave it as 4 times 2 to the x. Okay, and at this point, well, let's just make this a little easier to. I'm going to actually separate the 2 and the x. I'm going to write it as 2 to the x squared. Okay, and the reason for that is I'm going to actually do a substitution on my next step because I can see a 2 to the x there and a 2 to the x there, and we're going to do a substitution. Before we do that, I want to get this written so that it looks like a quadratic. You know this is going to turn into a quadratic. So I'm going to subtract this for both sides. So I get minus 4 to the 2x. Sorry, minus 4 times 2 to the x. And then this was a 1. So that's a 1, so it's a minus 1 on this side. And that's everything's cleared out on the right side, so that's equal to 0. And now at this point, I'm going to do a substitution. I'm going to let a equal 2 to the x, just for the purpose of factoring. So I've got a squared minus 4a minus 1 is equal to 0. Now, I want to do it for factoring, but when I look at this, it looks like a fairly simple trinomial, but it's not factorable. There's no two numbers that multiply to -1 and add to -4. So what do? We use the quadratic formula, which should be obvious by the title of the question. Okay, so I'm going to put a little note here, quadratic formula. I'm not going to show all the steps, but if you use quadratic formula, you get a is equal to 2 plus or minus root 5. So there's two solutions. That's what we always get when the quadratic formula, when this is a positive discriminant here. Okay, so I'm going to split this into two answers, and at the same time, I'm going to substitute 2 to the x back for a. So I get 2 to the x is equal to 2 plus root 5. And then the other one will be 2 to the x is equal to 2 minus root 5. Okay, and again, make it clear that that's one term there. I'm trying to solve for an exponent. So what do? We change it to logarithm form. So the x is the exponent, so that's how our logarithm equation starts. The exponent is equal to the log of the base 2 of 2 plus root 5. And over here we get the exact same thing, except that's a minus sign. X is equal to log base 2 of 2 minus root 5. Okay, now you might think, oh, that's good, we got two answers. One of the things we have to do when we are working with logs is make sure that all the solutions are valid solutions. And the biggest criteria is when I'm taking the log of something, it has to be positive. So I look at both of these, check to make sure that they're positive numbers. So this is, obviously positive. But root 5 is, I don't know it offhand, but it's something like, let's say 2.2. So 2 minus 2.2 is negative. So all of a sudden, this is not a valid solution. So no solution. I'll put the reason here. Or invalid. You can't take the log. So no log of negative numbers. Okay, so that's not valid, but this is. Okay, so if you're trying to figure this out on a calculator that doesn't have that functionality, you use the change of base again. Okay, I'd probably like you to do it anyways, even if you have one of these advanced calculators, just so you can do it. So this is going to be the log of 2, and you have to put this in brackets, 2 plus root 5 over the log of 2. And that's going to be approximately equal to 2.08. So there's our answer. Okay, so this is a tricky one. This is a technique that you just have to know. You recognize, I got a negative exponent there. How can I clear that out? I can multiply it by something that will eliminate it, at least either make it positive or 0. So that's what we did. Then we did a substitution, and we had a quadratic equation. Couldn't factor it, but we used quadratic formula, and got two solutions. One of them was invalid. The other one gave us our one and only solution. Okay, so there's a couple more techniques here. Definitely you have to know them, and you have to recognize them when you see that style of question. Okay, so I got some homework for you to try out. Make sure you get lots of practice on these. Part of the big, one of the most important skills is recognizing, looking at a question going, oh yeah, I remember this, I'm going to try that the technique that was used for that, because you can't just try any technique and expect it to work. that doesn't happen all the time. Okay, so try the homework, and we'll see you at the next lesson, which will be our last lesson for solving exponential and logarithmic equations. Have a great day.